Welcome to the Charterhouse Pre-Sixth Form course. I'm the Head of Physics, Mr. Massey, and in this video I'll be discussing problem solving and discussing how we might extend what we've done previously on force by looking at more than one dimension, using some of the trigonometry that you've learned. We'll then look at a few problems. The first I'll take you through, and then the remaining two can act as assignments as a takeaway. What I'd like to do first is talk about vectors. So a vector is a quantity with both size and direction, and in two dimensions, as we've got here, we can split a vector, which is represented by this red arrow. This might be, for instance, a force, so 5 newtons, in a particular direction. We can split it into two components. Now, you may have done this in maths. You can think of these axes as being the x-axis and the y-axis. You can think we're going 4.3 units left to right from here to here, and then we're going 2.5 units upwards. Now, if you use Pythagoras, you can relate the lengths of the opposite here side and the adjacent side relative to this angle of 30 degrees. And what you should find is that if you square them both and add them, you get the hypotenuse, which has length 5 in this case, squared. So the vector and its components, the horizontal component and the vertical component, form a triangle which obeys Pythagoras' theorem because it's right-angled. Okay, now what we can do is work out how you can actually calculate these components. So we'll be using x and y coordinates, and what I'm going to do is I'm going to draw this triangle to the side here. So we're going to have my length 5 hypotenuse. We've got this 30-degree angle here and a right angle. So what we're interested in is finding this side, which I'm going to call Fy, the vertical component of my 5 Newton force, and then the horizontal component is going to be Fx, the horizontal component here. So we've got x and y as our axes. Now we know, hopefully, from trigonometry, and I'm going to remind you, that opposite over hypotenuse is equal to sine of theta, where theta is the angle which is opposite the side we're interested in. So in this case, our opposite is Fy. So we've got Fy over the hypotenuse, which is 5, equals sine. The angle theta, in this case, is 30. So we have that f of y, if we rearrange that, is 5 sine 30. Similarly, for the horizontal component, we know this is the adjacent side, and we know that adjacent over hypotenuse is cos of the angle theta. So we know that f of x, which is going to be the length of this adjacent side of the triangle, divided by the hypotenuse length, which is 5 newtons, is equal to cos 30 degrees. If we rearrange that, we get that fx equals 5 cos 30. Both of these equal, well, that equals 2.5, and this one, this horizontal component, is 4.3 to two significant figures. Okay, so that's how you work out horizontal and vertical components. You simply use the fact that the opposite component, in this case Fy, is the hypotenuse multiplied by sine of this angle, in this case 30 degrees. The adjacent, the component which is adjacent to this angle, 30 degrees, you take the hypotenuse and multiply it by cos 30. This is all summarized in this slide, a bit more neatly. Of course, you can pause the video and have a look at that, and even re-watch what I've just gone through. Down here, we can see that we have the diagram again, slightly less cluttered. And this summary slide down here shows that if we have any vector, in this case, we're using f because we're dealing with force, but it would work for velocity and acceleration, any vector, we can find the vertical component by taking the size of the vector f and multiplying it by sine theta, where theta is the angle as marked. Okay, so we're interested in what the opposite side. Okay, so this is the opposite. Hence, you do hypotenuse F times sine theta. The horizontal component in this case, we want the adjacent side because this is the angle we've been given. So it's F, the hypotenuse length, times cos theta. This is going to be useful. What I'm going to do now is I'm going to play a video of me talking about problem solving, and then we're going to apply both what we've just learned and my problem solving recipe to a real problem. Okay, welcome. What I'm going to do first is quickly go through the points I've listed here, which are sort of a recipe, if you like, for solving basic physics problems. Now we're going to be looking at problems involving equilibrium, so situations in which an object is at rest or moving at constant velocity, but we'll be looking at an object at rest and applying Newton's first law to that situation, i.e. all the forces have to be balanced, resultant force has to be zero. Okay, so let's go through these one by one. Read the problem. You need to read the problem carefully, make sure you know what you're being asked, what information you're given. You want to draw a free body diagram, which is a diagram which shows all the forces acting, their relative sizes and directions, nice and accurately, so that you can then use that to help you when you come to the later steps. Okay, so it's basically a force diagram. Label the forces, so any information that's in the question which is going to be useful, size of force, direction, angles, lengths of objects, add those into your diagram. Then you can apply some physics. Now, if we're talking equilibrium, we might be considering the forces acting vertically or horizontally, making sure that they add to zero, taking into account the direction of the forces. If we were doing a question involving acceleration, we might use Newton's second law, which you're probably familiar with. Once you've set up, applied the physics and hopefully got some relationships and perhaps equations that you can use, then you can solve those with a view to finding what we have been asked. You need to make sure that you answer the question clearly. You know, for instance, you might do a calculation and have an answer with a unit. You might need some short explanation to describe what's going on and why you've taken the approach you have. Finally, you need to check your calculation and your reasoning before feeling that you've finished. Okay, now we're going to look at a problem. Indeed we are, and I'm going to go straight to the next video clip in which I describe the first of our problems. From a ceiling, I'm going to suspend a 1.5 kilogram mass by 2 strings. And these 2 strings are going to make an angle of 30 degrees to the vertical. Question is, like the problem, is to find what the tensions are in the 2 strings. So what are the tensions in the 2 strings? What I'd like you to do first is step 2 and 3, copy the diagram quickly and label the forces that are acting on the mass in this situation. So pause the video and do that now. Okay, so if you do as he says, have a go at that, and I'll continue in 3, 2, 1. Now you've had a chance to do that, you can compare what you've got with me. So we've got the weight acting downwards, W. We've got a tension in this string acting that way, T2. A tension in that string acting that way, T1. Now, any system that's in equilibrium, and this is at rest, the resultant force has to be 0. You should have learned that previously. In physics, when we've got a 2-dimensional situation like we do here, we can consider, in this case, it's most convenient to consider a horizontal direction and a vertical direction. Consider equilibrium in both those directions independently, and then if both horizontally and vertically we have an equilibrium, then overall the system's in equilibrium. So what we want to do is take the two directions, horizontal and vertical, and write some equations down linking these forces using some of what we've done so far. Bearing in mind we want the forces to be balanced both horizontally and vertically. Remember that this tension, both of these tensions in fact, will have a component, vertical component like this, and also a horizontal component. Okay, so we can use this idea of creating a force triangle and the fact I've given you these angles, 30 degrees, to actually split T1 and T2 into components. So without me saying anything else, you might need to go back and rewind the video when we were resolving forces. Try to write two equations here and here, that link W, T1, T2 for horizontal and vertical equilibrium. Pause the video and do that now. Okay, so pause away, and I'll continue in 3, 2, 1. The key to this is if we expand this region of the diagram, we've got T1 acting and T2 acting at angles to the vertical, and I gave you that angle to be 30 and this angle to be 30. Both T1 and T2, let's take T2, have a horizontal component which is acting in the case of T2 that way, and a vertical component which is acting upwards. We can work out what those are because this is a right angle triangle, it's a force triangle. This is the opposite side. So in fact, if you use the approach we used before, you can work out that that's T2 sine of 30. And this vertical component, because it's the adjacent side of the force triangle, is T2 cos 30. And you can actually do the same for T1. The vertical component of T1 ends up being, and we can actually draw this triangle in a slightly different way, just to keep the diagram slightly clearer, is T1 sine 30 and T1 cos 30. So you can split both T1 and T2 into horizontal and vertical components using the method we did before. If you do that, you can say horizontally, well, horizontally we've got the horizontal component of T1 acting that way. Remember that W doesn't have any horizontal component because it's vertically downwards. So we're interested in only the horizontal component of T1, which is T1 sine 30. And that has to be balanced by the horizontal component of T2, which is T2 sine 30 this way. Now, you'll notice something here, and that is that the sine 30 appears on both sides, which means straight away we've worked out using physics that T1 and T2 have to be the same size, which might have occurred to you just intuitively, just because these angles are the same. Okay, but we've shown it. What do we have vertically? We have that W acting downwards must be equal to the sum of the vertical components of both T1 and T2. So the vertical component of T1 is T1 cos 30. And the vertical component, if we add to that the vertical component of T2, is T2 cos 30. Now, because we know T1 and T2 are the same, we might as well just say, well, let's just call that T. Because then, instead of having T1 and T2 here, we can just have this value which is the same, T cos 30 plus T cos 30. Then we've just got, if you look at these are the same. So in fact that tells us that W is 2T cos 30. And we can work W out, can't we? Because we know what the mass is. So, pause the video and write down the final answer using the information that I've given, or we've worked out so far, the values of these three forces. Okay, pause the video and do that now. Okay, so if I take over from myself, we've got that W is m times g. The mass is 1.5 kilograms. Let's take g to be 10, assume we're on Earth. So that's 15 newtons. Then we have that W is 2t cos 30. So if we insert the value for W we get 15 is 2t cos 30. So t is 15 over 2 cos 30, which, if I type this into my calculator, gives me 5 root 3, which is 8.6. 6, so 8.7 newtons. So we've got, and both the tensions are the same, so both T1 and T2 are 8.7 newtons. So that's that problem solved. Now what you can do is have a look at these two problems. So this first one involves a rucksack and is very much similar to the question we just did. So identify the forces, follow the recipe for problem solving that I went through before. You might need to rewind the video to revisit that. So you'll want to draw a force diagram, label the forces and so on. For the second question involving this crate, you'll want to label the forces acting, bearing in mind friction will be acting up or down the slope. You can decide which direction. And then choosing a set of suitable directions to resolve along. I would suggest not horizontal and vertical. There is another way you can, or another pair of directions you can use. I'll give you a clue. You want to try and minimize the amount of resolving you have to do. So as long as the two directions you choose are perpendicular, it doesn't matter if they are like this or they could be like this. Okay, so have a think, have a go at those two problems. I'm also going to add a sheet of questions for you to try with solutions to look at, to have a go at over the summer using some of this information. So you can treat that as the assignment for this pre-sixth form course. Thank you for listening. Goodbye.